This posting considers the boundary layer equations in more detail. Specifically, we're going to look at the physical meaning of them and a brief derivation. And we'll find out that the boundary layer equations, like the heat equation before, are really a form of conservation equation. And we remind ourselves that the goal of deriving these equations and analyzing these equations is to understand what the variation of velocity and temperature is throughout the boundary layer that describes the region at which a surface at a different temperature than the free stream and imposing a no-slip boundary condition compared to the free stream velocity influences the temperature and velocity field as a function of distance y away from the surface and a function of distance x along the surface. So we'll find that this variation in u and t can be described with three separate conservation equations. One for mass or volume if we consider an incompressible fluid, one for momentum, and one for energy, thermal energy specifically. Let's look at the conservation of volume first. So we're going to derive an equation for the conservation of volume. But we need to remind ourselves really of the constraints under which this equation is valid. And primarily, what we're interested in is situations where the fluid can be considered incompressible. So this is liquids or gases that aren't moving at an extremely high velocity, not moving at velocities that are a considerable portion of the speed of sound. Oftentimes we might make a rule of thumb to say maybe if we're less than 1/3 of the speed of sound. So we can derive the conservation of volume the same way we've considered the conservation of any other quantity. We're going to define a region that we're interested in, and we're going to be considering a steady state situation so that that region won't change its volume with time. So we're going to look at the total that enters into that region, in this case the total volume of fluid that enters in, and the total volume of fluid that leaves, and that's going to be equal to the change of what is stored in that region. Well, the region has a constant volume, so that change of stored volume is just zero. So now we just need to evaluate what enters in and what leaves. Well, the rate at which volume is entering into the system is just going to be given by the velocity times the area of the face that we're considering. And if we want to convince ourselves that this really is the rate at which volume is entering, we can consider any surface or segment of a surface with an area A and think about how much fluid passes through that surface in a given period of time, delta t. Well, that fluid volume that will pass through that area in delta t will be equal to the volume that would be traced out by that surface moving over a length that would be equal to the distance a particle would move from the starting point to the surface in a period of delta t. That length is just going to be u delta t. And so the volume that passes through surface A or a surface with area A in a time of delta t will just be equal to L times A, or A U delta t. So the rate at which volume enters this region, the volume of fluid enters this region from the left face is going to be the velocity normal. This velocity has to be normal to the surface we're considering. So the velocity normal to the left face, which I'm going to call u minus, we'll say that this is the x direction, this is the y direction, and this is the z direction. The velocity at that left face, u minus, times the area of the left face. That'll be equal to the rate at which volume is entering this region from the left face, and we can write the same expressions for the right face and the bottom face and the top face. So for the right face, we'll call the velocity u plus at that point. Remember, the velocity doesn't have to be constant, and in fact, that's what we're trying to derive, is the change in velocity. So we're trying to derive an expression that is related to the change in velocity. And so we'll say u plus times a is equal to the rate at which volume leaves the right face. Likewise, we can say volume enters the bottom with a velocity of v minus times a, and I probably should label these a's. We'll call this ax and ay, just to give them, to distinguish them, since we've given different dimensions for each edge of the box. And we can say volume leaves the top face with a rate of v plus times ay. And we're not going to consider any volume entering or leaving from the front or back faces. We could just as easily, but we're going to derive the equations right now in 2 dimensions because we generally don't care about the 3rd dimension, or we're interested in boundary layers that can be represented in a 2-dimensional form. So now we just need to write out this balance of volume in and out of our system, and take a limit as this region goes to very small dimensions, and we'll arrive at the differential equation describing the conservation of volume. So that summation is just going to look like the rate at which volume enters the left side, u minus times ax. Ax is going to be given by delta y times delta z, minus the rate at which it's leaving the right side. So I'm going to go ahead and write that u plus, times the area. Again, the same area for both of these, just delta y, delta z. And then I can do the same thing for the bottom and top faces. I can say volume is entering at a rate of v minus times ay, and leaving at a rate of v plus times ay, and ay is going to be delta x times delta z. And that's going to be equal to the sum of volume in minus volume out, and that's going to be equal to the rate at which volume changes. Well, that rate is 0. So far I've been talking about a rate. We could just as easily say the total amount that's entered in a time delta t. But of course that's not really going to matter because I have 0 on this side. I could always divide through by delta t, and in fact that's exactly what I'm going to do. So if I divide both sides by the total volume of my region of interest, that's just delta x times delta y times delta z, and I divide through by the time over which I'm considering the movement of volume, delta t. I can do that for both terms. I can also do that for the right-hand side, which of course is still 0. And if I cancel out all the terms that are remaining, or I should cancel out all the terms that are the same between the numerator and the denominator, then I'm left with an expression that starts to look like where we want to get to. We're going to say that the change in velocity between the left face and the right face divided by the length of our region of interest plus the change in velocity between the bottom face and the top face and the height of our region of interest is equal to 0. So I can rewrite this as the change in velocity along x divided by the length of the region that I'm interested in. And I probably should put a negative sign here because I'm saying the velocity on the left-hand side minus the velocity on the right-hand side. Normally that would be what we call minus delta. And I can call this minus delta velocity in the y direction, delta v, divided by the height of the region in y, and that's equal to 0. Well, if I take the limit as delta x and delta y go toward 0, then these turn into derivatives. I'm going to multiply the entire, both sides of the equation by -1, and we're going to end up with an expression that we had talked about last time, and you see in your book as our first boundary layer equation. So really, this boundary layer equation, again, we want to see what the physical meaning of each of these are. And this boundary layer equation is a physical expression of the conservation of volume.